create a parallel code. And I asked you to use a reduction clause, which is relatively easy. But as I mentioned earlier, during the class where people are in fact physically attending the class, I asked them to program step by step using the knowledge obtained throughout the lecture. So I'm going to show you a couple of different approaches how you can solve the problem. And then at the end, I'll show you the reduction clause that hopefully everybody got right. So this is an example of a code, parallel code that some people create as a first approximation. And you can see it looks quite ugly, honestly, but hey, you're using only what you learn. So here, basically, instead of accumulating values in one variable, I use an array of 4 elements. And I have to do a lot of preliminary work in order to split the workload between the threads properly. So I have an ID that obviously defines a particular thread, the ID of the thread. I also have a variable n that is responsible for a total number of threads allocated. You could imagine that requesting 4 threads doesn't mean that I get 4 threads. So I would like to carry the number of threads given outside of my parallel region so I can perform a proper summation. And that's why I'm doing that in the master master thread. So this line, if ID equals to 0, then n threads equals to n, basically helps me to take of the parallel region. Says I'm muted. Okay. Can you hear me still, guys? Okay, perfect. So one more thing. So I have a cursor, obviously, and I'm moving it. Do you guys see the movement of my cursor or not? Okay, so that would be the way I highlight something. Thank you. Okay, so I also have my array sum. Initially, I created it with some constant. Being it I'm writing in C, I just chose, for example, maximum that I'm going to request. Again, the system can give you less threads. So for example, if I requested for 4, but I only had 3, obviously I have one element in my array that's doing nothing. So I would like to make sure that I only utilize elements that are working. So that's why I'm zeroing the elements of the sum for every thread. So the thread number 0 will 0 its own element and so on. Why am I doing that? If you would like to calculate a product, for example, so here obviously you will not use 0, you would use 1 as initial value for your product. And I also define here a variable x. I define it inside of a parallel region, so it means it will be private, local to every thread. And I also define my step size. So now I just have my for loop, and each thread is writing in its own element of the array. So remember, this is a first approximation, and when students are usually creating that kind of code, they have never heard of fault sharing, and they're surprised, of course, with the results they get. So after the parallel region is finished, I simply add all the elements in my array, of course, multiplied by a step size. And notice that I'm not using n threads as a constant. I'm using n threads that comes out of the parallel region. So in this situation, if I only got, for example, 2 threads, even if I requested 4, let's say I get only 2, I would only perform summing over these 2 elements. Again, it's important because if by default, let's say you get an array and values are let's say some garbage or maybe one or zeros, and I perform, instead of summation, I like to calculate a product. I cannot just go over every element of the array, because it will really skew my value. Of course, if it's initialized with 0 and I add something to my pi, it doesn't really change anything. But if you have, for example, a product, it will affect your total value. So any questions regarding this code? Okay, so if some questions arise during the presentation, just send us a chat message. So the next step is to obviously confirm that the code works and it actually does something good. Well, I'm running my code with multiple threads. So I used one thread to emulate the serial performance. And I also would like to run it with 2, 3, and 4 threads. I have in total 4. Okay, I have 2 physical cores, and with hyper-threading enabled, the computer thinks I have 4 threads. So it makes sense to run my calculation up to 4 threads. If I use more threads, it means just threads will be interfering with each other. So 4 is kind of max that I would like to check. And you can see that with one thread, just running a serial code, it takes about 10.8 seconds. With 2 threads, although it's taking 9.4 seconds, it doesn't seem like it's a big drop. So does it make sense to write all this code just to save a second? Well, with 4 threads, it kind of gives a boost, but not the kind of boost you're expecting from the code that's supposed to be 4 times faster. So that's why we need another approach. So the question is, how does the nth threads work? Okay, so if I have a serial code, meaning that I only have one thread, I always have a master thread. I always have a thread with ID 0. It always exists. So it means that I can't put here if ID equals to 1. The thread might not exist, but 0 always exists. So if ID equals to 0, if that thread is master thread, then n threads would get a value of n. Zoom has a lot of windows, just have to move them. So notice that int n threads is defined as shared. It means if I modify here a value, it will be carried outside of the parallel region. So the value here will change it globally. But I'm only allowing one thread at a time to change it. Sorry, not one thread at a time, just one thread. Only master thread can change it. So there is no race condition here. If the thread has an ID of 1, it just skips this part. It doesn't even know that it has to do something. Master thread changes the value of n threads. And now I know how many threads were actually in fact allocated. So yes, I asked for 4 threads, but if threads only 3 threads were given, I know that by reading the value of n threads. So as an alternative, you can use, of course, the master thread construct, pragma OMP master, that will reserve only the right for the master thread to change this particular value. Again, it's the beginning of the usually course, and I introduced this construct later, but indeed you can apply the master construct here as well. Okay, so if it's clear, let's just continue with our examples. So of course, as we already know, we facing the false sharing because the elements of array are so close. Both of this, so this array would be shared between multiple cache lines. So in order to make sure that they're consistent, the cache line would be constantly invalidated, and this causes obviously the slowdown. So the solution to that is to pad our array. So basically do the same thing by putting the elements far apart. But instead of writing element, let's say, into the 0th element, then 16th, then 32, and so on, I simply padded it by making the array multidimensional. So I'm adding the second dimension here, which is I'm not going to use, is just to add these paddings between the elements. And just by simply adding here and here, well, and obviously here, I'm getting rid of false sharing problem. That's all it is. The difference between this code and the previous one is that I'm using now simply 0th element in my second dimension, and it helps us to improve the performance. Again, you can do what we've done in the class, where you just write in an element, for example, 0th and some other element that's far apart. That's totally fine. Or you can do something like this. Neither of these approaches are really good because there are better constructs to use when working with OpenMP. So what's the question? No, solutions will not be available on the website. So because these are solutions that are kind of intermediate anyway. The last one is the one that you're interested in. So now let's compare the performance. So this is the first version with false sharing, and the second version is without false sharing. Look at the difference. So with one thread, it runs about for the same time because, well, obviously there is no speed up. But even with with just 2 threads, the performance is almost half of the performance with one thread. And with 4 threads, I'm getting almost 4 times boost in performance. So that's what you probably will be looking for in your code. Again, this code is well parallelized. I'm not really waiting for synchronization a lot. So in your codes, you might not get significant speed up, but it should be quite reasonable, because otherwise, why even bothering implementing it otherwise? So you see the drop for 4 threads from 6 seconds to 2.8. That's a big boost. Now, after we introduce synchronization constructs, of course, there is a better way to write the code. So here I'm again requesting 4 threads. But again, I don't know how many threads are given, so I'm querying it. So OMP get num threads. So now n has the number of threads given. And then I'm performing my summation. Notice that the sum variable is defined within the parallel region. I have this double sum definition inside of the parallel region. It means the sum variable is private to every thread. It's not shared. It's not defined here before the parallel region. So it means that every thread is performing some sort of summation, and it's performing part of it. So instead of running a for loop from the beginning till the end, I'm taking every other element. So if ID is, for example, 0 and number of threads is 4, well, obviously I will take the elements from the for loop that are 0, 4, 8, and so on. So I'm skipping several elements, and then I'm taking the element from the for loop. Then I'm skipping again, and I'm taking an element, and so on. So I distribute the workload between the threads manually. I'm doing it myself. After every thread calculated the sum, I have a critical section where I'm updating my pi variable, which is the shared one. So I'm saying only one thread at a time can update. I'm getting rid of race conditions here. And sum is local to every thread. So I basically, if I have 4 threads, I have 4 sums that are being added to the pi value that is shared across the threads. And then I'm simply printing on the screen. If I compare the results in performance, you can see that the padded version and with the critical section are quite similar. It's still very, very fast comparing to our first approximation. And it's as good as the padded version, but you can see the code is cleaner. Any questions so far? So why am I using long instead of int? Simply, if I look at my original code, I define n as a very big number. Okay, so honestly, I'm doing this quite artificially. You don't really need that number to calculate the pi value. But the problem is that I need a code that's simple enough that you guys can play with. And yet it loads your computer long enough so you can see the speed up. If you just here define, for example, that I would like to iterate over 1,000 elements, you get a result in like half a second. So you don't really, so even if you split the workload between 4 threads, the drop will be still considerable, but merely visible when you run your code. If I increase the value, of course, I'm slowing down my code. I'm slowing down it artificially to make sure that you get to an amount that kind of is painful to wait, but not maybe too much. Because if I keep adding zeros here, so basically I'm keep adding iterations to my loop, I can make it run for maybe a minute or 2 minutes. Obviously, we have different computers. It might take longer, it might take faster on your machine. My intention is not to make you wait for 10 minutes for the code to finish. So I chose about 10 seconds on my machine. So it might be 20 seconds on yours, maybe 8 seconds. So it's about the same. So this number here is chosen just to make your code a little bit slower so you see the speed performance with your parallelization. Now, this number is quite arbitrary. And if I make it too big, I might be out of the range of the int values. So if you're aware, C is a statically typed language, meaning that you have integers that are go from like, I think, -2 billion to 2 billion. And then you have long if you need a value more than 2 billion, and so on. Okay, so there is a limit. Thank you. So yeah, you can confirm what other limits are. So if I potentially can go outside of my limits, that basically will cause an overflow, and it definitely does not help to get a proper result. So since I was playing with the number, and you can play yourself, you can adjust this n, for example, because I'm running my code up to this number. You can make it larger, and long should still carry you through your calculations. So obviously, if you're making smaller calculations, you don't need long. You can just use int. Okay. Sometimes long is not enough. You can just do long. It will give you a really large number. In your particular computations, your computations might be just heavy. So you might not have a lot of iterations in the loop, but each iteration takes like 5 seconds. I also seen that. That's also possible. But our computation in the for loop is very, very fast. It's literally just a couple of operations. I can add a sleep command as well to test the performance, but I chose just to increase the number of calculations. Okay, so if there are no other questions, I'll show you the reduction clause. I looked at the assignments, and it seemed like most of you got it right. So basically, the first thing I did is I put default none. And obviously, breaks the code. So I had to decide whether I put variable as a shared or a private. Well, with the variable h, I decided to go with the first private. You can make it shared as well because it's only a read-only. You're not really writing anything into it. X, however, is being modified constantly, so I made it private. Why didn't I make it first private? Well, because I didn't initialize it in the first place, so I don't really care what the value is in it. I can also define it inside of the parallel region. That's also fine. I don't need to initialize it. I'm sorry, I don't need to define it in the for loop. Otherwise, it kind of defeats the purpose, but optimization should take care of it anyway. In any event, I made it private because I'm constantly redefining the value, as you can see here. And the last thing is, of course, the reduction. I have a sum variable, and I'm going to add values to it. So that's the reduction clause. So after you went through the pain of going through this padded version and the first approximation and then the critical section, you can see the difference in your code. This last version really doesn't require you to modify a lot. In fact, you just have to add one line. And if you want to make your code back serial, all you have to do is just comment this pragma and comment the include omp.h, and you're back to the code that you had before. So as you can see, with very little modifications, I was able to parallelize my code quite efficiently, which I can show you through the calculations. So you can see that the last one is as fast as the critical or a padded version, with only just basically one line of code. So hopefully all of you got similar performance. I noticed not everyone submitted the performance test, but hopefully you did it yourself and you saw the advantage of the reduction clause. I also noticed a couple of you submitted TXT files. When you write your code, it's better to put a proper extension. So if you're writing a C code, just make it .c. If you're writing, let's say C++ code, make it like CPP or CXS or CC, whatever is convenient for you, but just don't use TXT. TXT is good for just plain text files that, I don't know, you can write maybe your story or a poem, but not for the source code. So because if you give it to someone else, they might be confused how to run it, what is it, and I saw a couple of people doing that. So just bear it in mind. So any questions? So the attendance number for today is 2. Please make sure that you do this right away. Don't wait for the test to expire. Yes, the first column was the false sharing column, because we wrote our first approximation thinking, well, since threads are writing in the same value, how do I get rid of it? Well, I create an array, and every thread is writing its own element. That potentially that indeed removes the race condition, but now you create a new problem that is false sharing. But you see, if you're not aware of false sharing, you might think that you still got a result because you're down from 10 seconds to 6 seconds. So there is indeed an improvement, but it's less than half with 4 threads. So if you see your code indeed speeding up with more threads, but you don't get a significant performance boost, most likely you're experiencing false sharing or other problems in your code. I noticed from my experience that the biggest boost you get from 1 to 2 threads. So this one is usually very close to really half. After that, you get a worse return on your thread investment. So remember that when you run your serial code and then you switch to just simply 2 threads, you should see pretty close to half of the drop in the execution time. After that, it doesn't really follow the linear speed up, but this particular 1 to 2 threads usually gives the best performance boost. Okay, previous slide. Yep. Any questions? So this slash sign here is simply because I needed to break the line. The whole thing didn't fit on the slide. So this is the way you can break the line, and the compiler still sees it as a one long line. So if you are curious, you can take the code and, for example, you can modify n here. You might see your code significantly slower or significantly faster. Again, feel free to play with it. Slide number 60. Okay, okay, so in this situation, we don't choose the number of threads. In the previous example, since I had to create an array, I had to tell C how many elements I want. I did not want to use the malloc function to allocate the things in the heap, simply because I wanted to use as simple code as possible. So I used the static allocation on a stack. So when you see here, I'm creating, for example, an array, but I'm saying that my array will have up to 4 elements. I'm limiting right away. So this is not a best approach to begin with, but it's good enough to fit on a slide. On my last slide with the reduction, I'm simply relying on how many threads the system will give me. If I have 4 cores computer, technically the system should give me about 4 cores. Most of the time you will get 4 cores. Actually, very rare you can see anything below that. You usually, if you request a reasonable amount of threads, you get it. So again, I can also use an environmental variable to change that. So I can compile this particular code once with my reduction. And now I'm going to scroll all the way to somewhere in the beginning. Just give me a moment. I'll show you the environmental variable you can set. Okay, so here you can see that I can compile my code once, and then I can just change the value of the environmental bash or your shell variable OMP num threads with how many threads I want my code to run. If I just set it up to, let's say, equals to 1, I basically get a serial code without needing to comment anything inside of my code. So you basically can run your code with OMP num thread with 1, 2, 3, 4, and you will see the difference in the performance. No, I wasn't going to upload any slides. So this is kind of an assignment, and we usually do not share the answers with public because the recording is available online. So if you want to listen, you can always go back and re-listen to it. But slides are also uploaded, so we want to keep it a little bit private. So please take a look. And again, you can just listen to recording again if you want it. So the OpenMP code is looking for this OMP num threads variable. Okay, it knows it's supposed to exist. It's a particular special word. So obviously, if you define in your, you say you're creating your bash script, chances are you wouldn't call a variable OMP num threads. It's a very unique name. So it's reserved for OpenMP. Of course, you can define a variable, but it will potentially overwrite. Well, actually, you can use it for other purposes if you want, but it is reserved to be used with OpenMP, and OpenMP will look for this variable. If it's not set, it will just go with the default value whatever system gives. So how many cores are there? If it's set up for a particular value, it will use this value. Well, if your time remains constant, then we need to look at the code and see what the problem could be. Well, it means that there's a problem in the code. Or which one, slide 60? Or you running the same code? Are you sure you have OpenMP activated? Do you see the difference between serial code and with 2 threads? Remember, you have to compile it with the flag gcc -f OpenMP code. If you omit the flag, it will be serial code. Well, first of all, you have a race condition right there. Your X is defined outside, so it means every thread is writing to X. You might get a proper result once in a while, but it might not be consistent, it's not guaranteed. So you have a race condition with X. So you need to maybe make it private or so. You guys, I think, can share the screen. I really don't know. Ramses, just do your thing. I have to terminate my sharing for that. Yes. Oh, I see. Okay. Okay. So if someone wants to share, please just go ahead. Okay, so that's the code. Okay. Well, try running it with OMP num threads 1. No need to recompile anything. So you can see the difference. It takes 17 seconds. So your serial code takes 17 seconds. And when you use OMP num threads 8 or whatever maximum you got, you get speed up quite significant, over 4 times. Always remember that you can just do a print statement in your parallel region where you can print on the screen how many actually threads were allocated. if you're concerned whether you get any actually threads or not. Okay, now I need to check the chat. What do you mean the code is exactly the same? The whole idea of using the variable OMP num threads is you don't have to change your code. I don't know. Are you sharing the screen or someone else? How does it work here? Oh, you're sharing the screen. Okay, so you just showed us that with one thread, you get 17 seconds. With equals to 8 or whatever it is, you get a speed up. Yes, by default, if you don't specify anything, if you don't set the variable, in fact, you can run your you can type unset OMP num threads, and it's like variable doesn't exist. So OpenMP will simply proceed with whatever number of cores are available. So you don't have to set the variable if you're okay with the number of cores. But first, let's do export OMP num threads equals to 2. Make it 2. And run your code. Don't need to recompile, just time it. Yeah. The whole idea that you don't have to recompile anything, because some codes are very, very, like, it takes hours to compile. You definitely would like. So you can see that you had 17 seconds and now it's 8.6. You have a reduction in half. So it all works. You might not get 8 because you only requested 4 cores. So if you start increasing number of threads, you can see the diminishing returns. So if you do, let's say 32 or 64, you barely get any. You probably will get actually slower code because there's more time into creating threads than in fact they're working. Okay. Okay, so that's good. Any other questions? So first of all, your computer might have 2 cores, but in fact, with hyperthreading activated, enabled, you get 2 threads per core that will not interfere much with each other. You have to think that you can request as many threads as you want, but only 4, let's say, cores at a time can work to the full capacity, because you only have 4 cores, only 4 threads can operate at 100%. So by default, yes, if you run your code, if you have 4 cores on your computer, you will by default get 4 without defining anything inside of your code. So hyperthreading is basically the feature that Intel processors have, and I think AMD is called something else. But basically, all modern processors, they have ability to run as twice, like they can double the number of threads. So basically, if I have a Niagara node with 40 cores, I can actually run up to 80 threads without really interfering with one another. It doesn't mean that I really get a boost from 40 to 80, like double in performance, but it is actually available for you on the system. Notice that the biggest performance speed up you get still by going from 1 thread to 2 threads. Just by running your code, let's say on 40 cores, might not give you enough speedup because there is not enough work each thread is doing. So if you have, let's say, work that it takes 10 seconds, and you split it between 2 threads, now you have each thread working 5 seconds. But if you make it 40, well, you need to take 10 seconds and divide over 40. Do you have enough work, in fact, in each thread? So not always having lots of thread really helps to speed up the process. So basically, you will get a speed up, but it will not be as significant as this drop from 1 to 2 threads. So again, hyperthreading, it's done on a hardware level. So you definitely can get a certain boost, but it's not like the boost you get, for example, going from 8 or 4 cores to 8 cores. Again, as I mentioned earlier, when you're Niagara and you're running your code, for example, with 40 cores, you get a particular performance. You can give it a try with 80. You might get a 5–10% boost. If you're happy with it, stick to the 80 cores, 80 threads. If not, you can just keep it 40 as before. Okay, any other questions? What do you mean by parallelizing on cores from different nodes? If you're talking about if different nodes have different architecture, meaning that my computer has 4 cores and Niagara has 40 cores, there are different processors. So yes, indeed, you will have different performance on different computers. If you're talking about sharing the workload, you share the workload between different nodes, then it's a different thing. You need to listen to the lecture about MPI. Remember that OpenMP takes advantage of all the cores on your current machine. You cannot share your workload using just OpenMP with another machine. There are features that you can use GPU, for example, but GPU has to be on the same machine. So I know OpenMP standard is constantly expanding, and maybe potentially people will introduce something, but as to my knowledge, currently, OpenMP is limited to one machine, but it allows you to take full advantage of the available resources. So another, of course, approach to improve your performance and parallelize your code is to use MPI. MPI is a message passing interface, and I think Bruno is going to talk about it next week or so. So if you're interested in that, please attend the session. I'm sure it will be very, very interesting for you. It allows you to split the workload between multiple machines, between 1,000 machines. It doesn't matter. Okay, in 2 weeks. So in 2 weeks, the course would be there. And I would believe it will be like from very, very beginning. So if you don't have knowledge, please listen to it. You can actually use MPI also on one machine. If you don't want to use OpenMP code, you can just create multiple tasks on one machine. So, but these tasks are not limited to this machine. They can be launched on many other machines. Okay, any other questions? So another thing is that you can always combine launching, for example, an MPI task on this laptop and using OpenMP to take full advantage of this machine. And then the second MPI task you can run on another machine, another computer, and use OpenMP there as well. But this is a well-advanced code. It's called a hybrid code. And hopefully, if you need it, you will be able to get there. Any other questions? So we are having this session today, so you can ask any questions that you might incur during this assignment. So please feel free to ask. You can share the screen if you want. We can help you remotely as much as we can. Okay. So what is your question? Okay, so can you show us what this kind of performance you're achieving? How slow or fast it's running? Well, what is happening when you specify in static, you have to understand that your n variable define n, I don't know what is that, 1, 2, 3, like a million or so. It means that each thread is working on one iteration at a time. There is time involved into basically allocating the thread and so on. So your for loop naturally will run faster just without any parallelization versus using the static schedule with a chunk size of 1. So what is happening if you don't specify a schedule, or at least you don't specify the chunk, or the size of a chunk, your for loop is going to be split amongst the threads. So if you have, for example, 4 threads, then each of the thread will work for about quarter of a million elements. If you do this one by one, it means that the thread has to finish and take another iteration 250,000 times each thread. If you specify without chunk size of 1, the thread is not going to finish. It's going to just keep iterating 250,000 times. You can try changing the schedule static, for example, from 1 to, I don't know, 100,000, and see if you get a speed up. Not always necessary the default chunk size is good. You might get a better speed up by, for example, using 300,000 or 100,000, or maybe even 10,000 elements each. It's simply because the workload might be not even, meaning that some threads finish earlier than others, some iterations take less time. So in this situation, playing with the schedule can give you better performance. But because we have so many iterations, so we have 1 million iterations or maybe even more, using using schedule static with a chunk size of 1 will really slow down in this situation. Try to use a larger, significantly larger chunk size. Remember, the workload is split between the threads. Does it answer the question? Yeah, you can just play with the different schedules and see which one gives you the best result. Well, when you specify default none, you will get error just because some variables, like the system doesn't know whether variables should be private or shared. By default, everything is shared. You can actually specify default shared, and that's the default behavior. But when you say default none, meaning that you have to specify everything. So these are the errors you're talking about? Potentially, maybe there are more variables that meets the I. You need to make sure you took care of all variables. What about n? Where is n? Is it defined? Okay, so it's defined. It should work. What about this variable sum underscore th? Where did you define it? There is no definition anywhere, or at least maybe just a text editor hiding characters. In your for loop, the second summation sum underscore th doesn't have any definition, so maybe that's the error you get. Oh, sorry, I see it. It's double on outside. I see it. Well, if you show us the errors, then we can help you more, because it's really like, and also guys, when you send us an email with help regarding your codes on Niagara or anything, we're very welcoming your questions. It's just we sometimes get a email saying, well, my code doesn't work, and that's it. Or I ran the program and I got an error. We really need the error, because we can't really predict what exactly is happening with your code. So please tell us what exactly is happening so we can help you fix it. So if you can compile your code so we can look at the errors, I think that might be beneficial. No, you can't put num threads in your for. Your Pragma OMP4 is inside of a parallel region. So let's look, what do you mean? So if you have Pragma OMP, the first one, parallel, that creates a team of threads. That's called a team of threads. But you didn't specify how many threads you want. Now inside of your parallel region, you have a for loop. And now you're saying, well, I want 10 threads. Well, it's too late. You already have a team of threads created, and you cannot in OpenMP create thread inside of a parallel region. So you have to put num threads equals to 10 where you start your parallel region. So that was the first error I noticed. I don't know if you want to fix it now or show us again. Okay, go ahead. I believe you need Pragma OMP parallel 4. Do you have the parallel word in it? You need Pragma OMP parallel 4. Yes. Try recompile it. Okay, so your curly braces must be on a new line. You cannot have it at the end like with a for loop. That's a different limitation of OpenMP, but make sure that your curly braces goes on a new line. Okay, try again. Okay, so now you have more explicit errors as a H is predetermined shared for shared. Let's look at your code. Remove the word const from double H when you create the variable H. Okay, try recompile it now. Okay, remove it from shared, the sum. You don't need to put some. I think it should, even with default none, it should just work because it's in your reduction clause. Just a sum variable from shared. Okay, try again. We gotta look again at the code. There's some curly braces. Okay, this one I'm not sure. There's some mismatch with opening and curly braces for statement. Oh, go back. Oh, okay, open it. Open your code. That's the reason. Okay, so when you work with pragma OMP parallel for, this command only works for the next for loop. So when you cannot have pragma OMP parallel for and then something else. It's got to be a for loop. So remove your curly braces before and after for loop. If you need to define something before or after, you have to create a parallel region. Then you make your definitions, and then after that you put pragma OMP for, and you start to for. So pragma OMP for must be followed by the for loop without any curly braces. Now try recompiling it. Yes, so definitely curly braces are helpful, but pragma OMP4, I think it's the only construct that requires you for loop right after that, so you don't really need that, and I guess they removed it. So as you can see, it works. Okay, any other questions? Well, first of all, you're printing something on the screen. That slows down your code significantly. If you want to speed up, the first thing, don't print from every for iteration. Just terminate the other one and use the other terminal. There's no need to navigate. Make sure your other code is not running, because then you will have two heavy codes loading the computer. Did you close it completely, or you just minimized it? Okay, just type in your terminal TOP, top. Enter. I guess it's not running anymore. Okay. Yeah, just type X. Oh, sorry. Press Q for quit. Okay, so now you're out. That's how you can check whether your code is running or not. So now you can try recompiling it. Well, it was quite fast. You were talking about 20 minutes? Yes, printing slows down it significantly. You're talking about multiple threads accessing one resource. It's like maybe you and your parents sharing a car. You need to go to buy groceries and they need to go print something. So you gotta wait. And the same is happening with the screen. It's a shared resource, and only one thread at a time can use it. And printing on a screen is a slower command operation to begin with. So you shouldn't probably ever print anything from the for loop, especially when it's like a million times, because there is no useful information there anyway. You might want to put like a if statement, like if counter equals to, I don't know, is 10,000, 20,000, 30,000, then I print something, because you want to limit the number of the amount of output you generate on your screen. Again, if your every iteration takes a moment or so, that's fine if you're printing. But if you are that fast in every iteration, because we simply just adding a value like a couple of times, it takes a nanosecond or something. So you get this a lot of output very, very fast, and it's not really beneficial. Okay, any other questions? Yeah, well, I guess it takes some practice and experience. Yeah, so when you print, of course, there is a conversion happening. So there is, just do it if you know that you have maybe 10, 20 iterations, or if every iteration takes some time and you want to have a log of your outputs. That's normally, that's fine. It's just that, are you going to look through a million lines? Probably not. And it slows down the performance regardless. Matlab comes with its own parallelization toolbox. Matlab is all proprietary, so I don't really know if they're using OpenMP or what are they using underneath the hood. It's been a while since I worked with Matlab, but you can integrate, I think, C code in it, so you can just like Python and C, you can connect them. And then your C code can use OpenMP, and you can use that, let's say, function in your Matlab. That's the suggestion I would have. If other guys have any experience with that, please let us know. Please, other questions? The languages that you are using probably have parallelization features in them. So you don't really need to go to OpenMP if you're working in, let's say, Python. Sometimes the speed up that you get by just using tools built in your language are enough to give you enough performance. I would suggest going to OpenMP really when you're desperate for more performance. Because remember that in OpenMP, being C, you have to explicitly write your loops. There are some tricks how to make your code faster, like for example, unrolling the loop. And they're not the best practices that we're not teaching usually, but it will make your code faster. But you probably should use all the other resources available before jumping into writing your custom code, and just use the tools that are available with Matlab first, Matlab or Python or R, whatever is there, and then if the performance boost is not good enough, then you might try something else. If you're working with C, of course, it makes sense to just continue using OpenMP there. No, all the computers on the market are NUMA, meaning that they have a certain architecture and certain processors are closer or further proximity-wise from the memory. It means that system might favor a closer processor than the one that's further, and so on. So I think there is one like Cray supercomputer a long time ago invented that had this SMP architecture, but there are literally like one or two supercomputers that were created that are more close to symmetric multiprocessor than NUMA. So you don't really have a choice. The operating system is really controlling your computer. You can only tell the system what you want, and then you're at the mercy of the system. It might even give you less threads, but you don't need really to worry about it. C gives you quite low level of the control. So when it comes to memory or processors, you don't really control which processor gets what. There are ways to do that through environmental variables, but you need to research that part yourself. You really don't need to worry about that whatsoever. So if you are interested in getting an account, there is a link. You basically need to find a professor, a PI, principal investigator, that can vouch for you, saying, yes, I know this person, basically sponsor you. It doesn't cost anything. It's all free. Let's always remember that everything is free. It's just a matter of someone making sure that they know they already have account in our system. Our teach cluster is just basically for teaching. And if you need to perform full computations, of course, Niagara is always available. Yeah, that's a good point. So OpenMP is limited to C, C++, and Fortran, but it does work on many platforms. So you can always recompile your code and it should still work great. Okay, any other questions? What do you mean compare with the root? What is root? Guys, if you know what the root in this situation is, please feel free to. I actually never heard of it, so I can't comment on that. Thank you for the link. We'll take a look at it. Well, we're in the same boat because I also just heard it today from you. So if someone knows, okay, so Ramses knows more about it. I guess if it will get more traction, we might get into it more. So definitely adding parallel features to your program requires you to rewrite your code. So if you're working with C or C++, give a try to OpenMP definitely. I would suggest if you're with Python, for example, there are libraries, of course, available, and it might give you enough boost without going to rewrite your code in C for that purpose. So again, just give a try to the tools that you can find in the language you're using. And if not, then of course C is always available. It's just in Python, if you are calculating something, which if you want to use OpenMP, you probably are calculating, just use NumPy or SciPy. They have a very good parallelization built in, and rewriting the code yourself in C will probably give you less performance boost, but you will definitely see a couple of days probably rewriting your code. Well, depends on the complexity, of course, of it. So try to use the modules that are already given to you. So that would be my suggestion. I think Julia has a nice way to parallelize your code with like one line or so. So having a slightly, I guess, more friendly syntax, you can, for example, try to calculate something in parallel in Julia and then transfer this data into your other language. That could be also an option. Remember that you don't really have to integrate your codes in different languages through the internal interface. You can simply write into the file, and maybe later you can get to it if you need, in fact. So there are different ways to improve your program. If you feel confused, what's the best way, just email us, and somebody with expertise definitely will help you improve your workflow. Okay, any other questions?